Tonight, we're going to look at the only galaxy outside our own that you can see with your naked eye, and at the fact that it is falling toward us at about 110 kilometers every second. That number is not a forecast. It is a measurement, and it is old. A man named Vesto Slipher wrote it down in September of 1912 on a photographic plate at a small observatory on a hill in northern Arizona, at a time when nobody on Earth yet knew that Andromeda was a galaxy at all. The light coming back from it was shifted toward the blue end of the spectrum. In the physics of the day, as in the physics of ours, that meant one thing, and only one thing. The object was coming closer. 110 kilometers per second is about 246,000 miles per hour. It is roughly 7 times faster than the fastest spacecraft ever launched away from Earth. Held at that speed, the gap between here and there still takes billions of years to close, because the gap is about 2.5 million light years wide, and that is the first thing worth holding on to. The approach began before there were people to notice it, and it will finish long after the last of us. It is not an event, it is a condition. And it has consequences that do not reverse. Once two galaxies of comparable mass fall close enough, gravity does not let go. Orbits stop being circles and start being long, stretched paths. The disks that took 10 billion years to flatten themselves lose the flatness in a fraction of that. And the shape you can find on any dark night in late summer, that faint, hazy band running from one horizon to the other, the Milky Way seen edge on from a seat inside it, stops being a shape at all. You are not looking at a permanent feature of the sky when you look at that band. You are looking at an arrangement. The stars are real. The arrangement is temporary. But is that arrangement actually going to end the way the headlines say it will? That is the honest question tonight, and the honest answer has changed twice in the last 15 years. By the end of tonight, you're going to understand exactly what was measured and when, why the answer became less certain rather than more as better instruments came online, and what the sky would actually do, stage by stage, over the next several billion years, in the versions where these two galaxies do meet. Before we get started, if you love exploring deep space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what is actually above you. On a clear, dark night in the northern hemisphere in autumn, high in the east, there is a smudge. It is not a star. It does not twinkle because it is not a point. Averted vision helps. Look slightly to the side of it and it brightens because the edges of your retina are more sensitive than the center. That smudge is cataloged as Messier 31. And it is the most distant object the unaided human eye can reliably see. It has an apparent magnitude of about 3.5, which puts it in the same brightness class as a modest star in a modest constellation. That is deceptive. The full extent of Andromeda on the sky is about 3 degrees across, roughly 6 times the width of the full moon. Your eye is not seeing 6 moons of galaxy. Your eye is seeing the bright core and nothing else, because the disk falls off in brightness so quickly that everything outside the center sinks below the threshold of human vision. Photographs recover the rest. You cannot. The story of what that smudge is doing begins with a single instrument and a great deal of patience. Vesto Slipher was working at Lowell Observatory in Flagstaff, Arizona, on a 24-inch refractor that had been built to look at Mars. Percival Lowell, who founded the place, was interested in planetary canals that turned out not to exist. Slipher was assigned to spectroscopy, which in 1912 meant spreading starlight into a rainbow and photographing it. And the photographing was the hard part. A spiral nebula is faint. Spreading its light across a spectrum makes each part of it fainter still. Exposures ran for many hours, spread across multiple nights, with the telescope tracked by hand against the rotation of the Earth. In September of 1912, he obtained the first useful spectrum of a spiral nebula ever recorded. By early the following year, he had 4 plates showing the same thing, and the thing they showed was strange. The dark absorption lines in Andromeda's spectrum, the fingerprints of specific elements, were not where they belonged. Every one of them sat toward the blue end. The shift was consistent. It was large, and when he converted it to a velocity, he got a number near 300 kilometers per second, moving toward us. Nobody had a category for that. The fastest stars anyone had measured moved at a few tens of kilometers per second. Slipher's nebula was moving an order of magnitude faster than anything in the local catalog, and it was moving the wrong way, toward the observer rather than away. The result was met with open skepticism, which is the correct reaction to a single measurement of an unprecedented quantity. It was also confirmed within a few years independently by William Wright at Lick Observatory and Francis Pease at Mount Wilson. The number held. What makes this worth pausing on is the sequence. Slipher measured Andromeda's velocity in 1912. Edwin Hubble did not establish that Andromeda was a separate galaxy, far outside the Milky Way, until 1925. For 13 years, astronomy possessed an accurate speed for an object whose nature was completely unknown. The measurement arrived before the meaning did. That happens more often in this field than the tidy version of the history suggests, and it is worth remembering when a modern result seems to arrive fully formed. The modern value, corrected for the fact that the Sun itself is orbiting the center of our own galaxy at about 230 kilometers per second, is that Andromeda and the Milky Way are closing on each other at roughly 110 kilometers per second. The raw number Slipher measured, near 300 kilometers per second relative to the Sun, is still correct. It just includes our own motion. The way a measurement of how fast a car is approaching includes the speed of the car you are sitting in. A spectral shift is an extraordinarily good instrument, and an extraordinarily limited one. What it measures is motion along the line of sight. Light from an object coming toward you arrives with its waves compressed, shifted toward blue. Light from an object moving away arrives stretched, shifted toward red. The size of the shift gives the speed of the approach or the recession with real precision for a bright galaxy to within a few kilometers per second. This is why Slipher's number survived a century of instrument upgrades essentially intact. What it does not measure at all is motion across the line of sight. Consider what that means for the problem at hand. 2 galaxies are approaching at 110 kilometers per second. That single fact is compatible with 2 completely different futures. If the approach is close to head-on, if the sideways component of Andromeda's motion is small, Then the two systems fall into each other, pass through, fall back, and merge. If instead Andromeda carries a substantial sideways velocity, the same approach speed produces a wide flyby, a slow gravitational dance at a distance, and possibly no merger at all for a very long time. The blueshift cannot distinguish between those two cases. It is silent on exactly the quantity that decides the outcome. This is a general feature of astronomy that deserves to be stated plainly because it explains a great deal about why confident-sounding claims get revised. We measure what light gives us. Light gives us brightness, color, spectral lines, polarization, and the arrival time of everything. It gives us radial velocity for free and transverse velocity almost never. To get sideways motion, you have to watch an object actually change position on the sky. And for something 2.5 million light years away, that displacement is so small that for most of the 20th century, it was simply beyond measurement. The scale of the problem is worth making concrete. Andromeda's sideways motion, as eventually measured, corresponds to an angular drift of a few micro-arcseconds per year. A micro-arcsecond is a millionth of a second of arc, and a second of arc is a 3600th of a degree. Put another way, the apparent shift of Andromeda across the sky over an entire human lifetime is comparable to the width of a human hair seen from several hundred kilometers away. That is the measurement the answer depends on. The technique that finally worked is disarmingly simple to describe and brutal to execute. You photograph the same patch of a galaxy twice, years apart, with the same instrument, and you measure how far the stars in it have shifted. The Hubble Space Telescope has one enormous advantage for this. It sits above the atmosphere, so its images are not smeared by air. Its point spread function is stable and well understood, and it does not change from decade to decade the way a ground-based site does. Between 2002 and 2010, astronomers used it to image 3 separate fields in and around Andromeda, going deep enough to resolve individual stars, and then came back and imaged them again after a baseline of several years. The measurement is differential. You do not track Andromeda's stars against nothing. You track them against distant background galaxies visible in the same frames, objects so far away that their own apparent motion is effectively zero. The background galaxies are the fixed marks on the ruler. Andromeda's stars drift against them. The drift, divided by the elapsed time, is the proper motion. The 2012 result, published by Sohn, Anderson, and van der Marel in one paper and turned into a full velocity vector by van der Marel and collaborators in a second, was the first direct proper motion measurement of a galaxy outside our own immediate satellites. The transverse velocity came out at about 17 kilometers per second. 17 against an approach speed of 110. That ratio is the whole 2012 story. A sideways component, that small means the orbit is very nearly radial, very nearly a straight fall. And a straight fall between two objects of this mass, from this distance, has only one outcome. The two galaxies pass through each other, decelerate, come back, and merge. There is one more thing about that 17 kilometer per second figure that matters, and it will matter more in a moment. It was not a precise 17. It was a best estimate with an uncertainty large enough that 0 was comfortably inside the range. The measurement was consistent with a perfectly head-on collision. It was also consistent with a somewhat glancing one. What it ruled out was a wide miss. In May of 2012, NASA published the result with a headline that said, "The Milky Way is destined for a head-on collision." The science underneath that headline was careful. The orbit integration in van der Merle's third paper gives specific numbers with specific error bars, and they are worth stating exactly because the popular version of this story has been rounding them off for over a decade. First close pass, 3.87 billion years from now, with an uncertainty of about plus 420 million or minus 320 million years. Closest approach on that first pass, about 31 kiloparsecs, which is roughly 100,000 light years, about the width of the Milky Way's bright disk, which tells you how nearly the two centers line up. Full merger, meaning the point where the two systems have settled into one object. 5.86 billion years, with an uncertainty of plus 1.5 billion, minus 700 million. So even the confident version was never a single date. And it was never 4 billion years to the finish. 4 billion years is roughly the first pass. The merger takes about 6. There is a second number in that paper that almost nobody quotes. The team ran Monte Carlo orbits, sampling within the measurement uncertainties, and in 41% of those orbits, M31 makes a direct hit on the Milky Way. Not 100%, 41. In the rest, the first pass is a near miss of varying width, followed in most cases by a merger anyway, because the near miss at these masses still bleeds enormous amounts of orbital energy into the two systems and brings them back together. It is worth being fair to the 2012 team here, because none of this was hidden. The paper states its uncertainties plainly, quotes them in the abstract, and describes the Monte Carlo spread in detail. What happened afterward is a very ordinary failure of transmission. A result with error bars entered a system that rewards clean statements, and the error bars were the part that did not survive the trip. The number that traveled was 4 billion years, stated flatly, with no percentage attached to it and no distinction drawn between a first pass and a completed merger. That distinction, merger versus direct hit, is where the last decade of confusion lives. The 2012 papers said a merger was very likely. The press said a collision was certain. Those are not the same claim, and the gap between them turned out to be exactly where the science was going to move next. To predict an orbit, you need 3 things: positions, velocities, and masses. 2 of those had been measured. The third had not. Weighing a galaxy is not like weighing a planet. For a planet, you watch a moon go around it and read the mass straight off Kepler's third law. For a galaxy, most of the mass is not in the stars. It is in a dark matter halo that emits no light, extends far beyond the visible disk, and is inferred only from its gravitational effect on things you can see: the rotation speed of the outer disk, the motions of satellite galaxies, the temperature of the hot gas. Every one of those methods carries systematic uncertainty, and they do not always agree. Published estimates for the Milky Way's total mass have ranged over roughly a factor of 2, and the same is true of Andromeda. For a long stretch of the 20th century, the standard assumption was that Andromeda is substantially the larger of the two. More recent work has narrowed that gap considerably. The two galaxies now look closer to equals, with the ordering depending on which method you trust. Older counts putting 1 trillion stars in Andromeda against a few 100 billion in the Milky Way have not survived contact with modern mass modeling. There is one elegant method that uses the approach itself, and it is old. In 1959, Franz Kahn and Lodewijk Volyer pointed out that if the universe has a finite age, and if the Milky Way and Andromeda started out moving apart with everything else and are now moving together, then gravity has had exactly that much time to reverse their relative motion. Run that backward and you can solve for the mass required. It is called the timing argument, and it was one of the earliest pieces of evidence that galaxies contain far more mass than their light accounts for. The timing argument is beautiful, and it is also fragile. It assumes the two galaxies are an isolated pair on a clean radial orbit. They are not. They sit in a group with more than 80 known members, and at least 2 of those members are large enough to matter. Which brings us to 2025, and to a result that did something unusual. It took better data than anyone had in 2012, and it produced a less confident answer. In June of 2025, a team led by Till Sawala at the University of Helsinki published a paper in Nature Astronomy with a title that left nothing to interpretation: No Certainty of a Milky Way Andromeda Collision. Their approach was different from the 2012 work in one specific way. Instead of integrating a small number of best fit orbits forward and quoting the spread, they treated the entire problem as a probability distribution. They identified 22 variables that feed into the outcome: the positions, the velocities, and the masses of every body large enough to matter. Assigned each one a realistic uncertainty based on the best current data from Gaia and Hubble, and then ran 100,000 simulated futures, each one drawing a different combination from within those uncertainties. Every simulation ran 10 billion years forward. Then they counted. In about half of those 100,000 futures, the Milky Way and Andromeda merge within 10 billion years. In the other half, they do not. Not merge later than expected. Do not merge inside a window more than twice as long as the 2012 estimate for the whole process. And within the specific window that the headlines have been quoting for 13 years, a head-on collision in the next 4 to 5 billion years. The probability came out at about 2%. 2%. That is the number that ought to be sitting next to the phrase, Andromeda is coming, in every article written since. The approach is real. The head-on crash inside 4 billion years on current data and current mass estimates is a 2% branch. It is worth being precise about what this study did and did not overturn. It did not find an error in the Hubble proper motions. It did not claim Andromeda is receding. It did not say a merger will never happen. Half of the realizations still end in one. What happens past the 10 billion year horizon the study covered, it does not quantify, and neither will I. What it said is narrower and more interesting. Given everything we currently know, and given honest error bars on all of it, the outcome is not determined. The local group is a system poised near a boundary, and small changes in inputs push it to one side or the other. The lead author put the situation in a way that is unusual for a press release and closer to how scientists actually talk. Predicting the long-term future of galaxy interactions, he said, is highly uncertain. And there is something ironic in the fact that with more precise Hubble data in hand than ever before, we are now less certain about the outcome than we were. That sentence is the intellectual center of tonight. The reason more precision produced less certainty is that the better data revealed that this was never a two-body problem. A two-body gravitational system is exactly solvable. Two masses, known positions, known velocities, and the future is a closed-form curve. It has been solvable since Newton. Add a third mass of comparable importance, and the exact solution disappears. The system becomes chaotic in the technical sense. Small differences in the starting conditions grow, sometimes slowly, sometimes fast, until two nearly identical setups end in entirely different places. The local group has at least four bodies that matter here. The Milky Way and Andromeda are the two large spirals. The third is the Triangulum Galaxy, M33, a smaller spiral bound to Andromeda, roughly a tenth of its mass but not negligible. The fourth is the Large Magellanic Cloud orbiting the Milky Way, and modern mass estimates for the LMC have gone up substantially in the last decade, high enough that it noticeably perturbs the motion of the galaxy it orbits. Here is where it gets specific, and here is where the two extra bodies do opposite things. M33 sits on Andromeda's side of the system, and its gravity pulls the pair slightly together. Including M33 in the simulations increases the probability of a merger. The Large Magellanic Cloud does something more subtle. Its orbit around the Milky Way is steeply inclined, close to perpendicular to the line joining us to Andromeda. As it swings around, it drags the Milky Way's center of mass sideways off the plane that contains the Milky Way Andromeda orbit, and sideways is precisely the direction that turns a head-on fall into a glancing approach, including the LMC decreases the probability of a merger. Neither effect is dramatic on its own. A galaxy a tenth or a 20th the mass of the main body does not throw it across the sky. But the outcome is sitting near a knife edge, where a difference of a few tens of kilometers per second in transverse velocity decides whether two systems fall together or sail past each other. Near a knife edge, small pushes are the whole story. This is why the honest answer is a distribution rather than a date. And it is why the answer will keep moving as the LMC's mass and the local group's mass budget get pinned down. It is easy to hear all of that as the collapse of a story, and it is not. Something important survived intact, and it is the thing the title of tonight's episode rests on. Andromeda is coming. The approach velocity, 110 kilometers per second of closing motion, is a direct spectroscopic measurement, confirmed independently since 1913, refined but never reversed. There is no serious dispute about it anywhere in the literature. The two largest galaxies in the local group are falling toward each other, and they have been for billions of years because they are gravitationally bound to each other and to the same dark matter concentration. The expansion of the universe pulls unbound structures apart. It does not pull bound ones apart. the local group is bound. On that, the science has not moved an inch. What is uncertain is not whether they are approaching. It is what happens when they arrive. There is a useful distinction hiding here between two kinds of astronomical statement, and once you have it, a great deal of science news becomes easier to read. The first kind is a measurement. Light came in, an instrument recorded it, a number came out, and the number has an error bar attached. The second kind is a model result. Measurements went in, a set of physical assumptions processed them, and a prediction came out, and its uncertainty is the combined uncertainty of every input plus every assumption. Andromeda's approach is the first kind. The merger is the second kind. The distance to Andromeda is a third example worth having, because it shows how a measurement can be improved rather than reversed. Edwin Hubble's original estimate in 1925 put the galaxy at roughly 900,000 light-years, which was wrong by a factor of nearly 3, because the class of variable star he used as a distance indicator turned out to come in two varieties with different intrinsic brightnesses. Once that was sorted out in the 1950s, the distance roughly tripled and has been refined steadily ever since. The number moved. The method survived. Both are legitimate science. They do not deserve the same confidence, and the difference between them is not a technicality. It is the difference between we saw this and here is what we think that implies over 5 billion years. If you keep only one habit of mind from tonight, that is the one worth keeping. When a claim about the deep future arrives, the useful question is which of those two kinds it is. The answer is usually available in the first paragraph, if the writing is honest. And here's the thing nobody likes to say plainly. A 50% answer feels like a failure, and it is not one. There is a strong instinct in science writing and in the reading of it to treat uncertainty as a temporary embarrassment, a placeholder that a better telescope will eventually erase. Sometimes that is true. The distance to Andromeda was uncertain by a factor of 2 in 1925 and is now known to a few percent. But sometimes the uncertainty is not a defect in the measurement. Sometimes it is a real property of the system, and the honest result is a probability that no instrument will ever collapse to a yes or a no. The local group appears to be that kind of system. Its future sits near a bifurcation where two paths diverge, and the initial conditions are not knowable to the precision that would pick one. Better data will narrow the distribution. It is not obvious that better data will ever eliminate it. There is also something worth noticing about how the 2012 result was received compared with the 2025 one. In 2012, the community got a headline it could use: destined, head-on, certain. And that headline traveled for 13 years, detached from the 41% direct hit figure buried in the paper it came from. In 2025, the community got a headline that is harder to use because maybe does not travel well. The second headline is closer to what the data supports. None of this makes the sky less interesting. It makes it less scripted. Somewhere in the next several billion years, this system does something, and the range of things it might do is wide enough to contain both a slow merger into a single smooth galaxy and a long, elegant near miss that leaves both disks bent but intact. For the rest of tonight, we are going to walk through the merger branch, the roughly 1 and 2 future in which they do come together, because that is where the sky does the most interesting things. Everything from here forward carries that condition, and I am going to keep saying so. The first thing to fix in that branch is the word collision, because it imports a picture that is completely wrong. The picture the word supplies is two solid objects meeting. A crumple zone, a shock front, debris. That is what happens when two things collide, and galaxies are not things in that sense. A galaxy is not an object. It is a population, a few 100 billion stars, held loosely together by their mutual gravity and by a much larger halo of dark matter, moving on independent orbits, separated from each other by distances that are enormous compared with their own sizes. A better picture is two flocks of birds passing through each other. Watch two large flocks converge and interleave. The flocks change shape. The individual birds do not touch. The pattern deforms, splits, reforms, and eventually settles into a different pattern, and every bird in it flew through the whole event without a single impact. That is much closer to what two galaxies do. Better still, think of two swarms of insects on a summer evening, each one holding a loose shape, drifting through each other and emerging changed in outline, but intact in membership. The deformation is real. It is severe. Gravity is a long-range force, and when a few 100 billion stars pass through the gravitational field of another few 100 billion, every orbit in both systems is rewritten. Disks warp, spiral arms come apart, long streams of stars get pulled out into the surrounding space and never come back. On a timescale of 1 billion years, the visible shape of both galaxies is destroyed. But the destruction is entirely a matter of arrangement. Not one star in either galaxy is likely to be struck by another. There is a reason the wrong picture is so durable, and it is worth naming. Almost every image of a galaxy merger that anyone has ever seen is a photograph taken from tens of millions of light years away, in which two enormous objects appear to be touching. At that scale, they are touching, in the sense that their outlines overlap. But an image compresses an entire depth of space into a flat plane, and the thing it cannot show is that the two overlapping regions are still, internally, almost entirely empty. The picture is accurate, and the impression it creates is not. That claim deserves more than an assertion, so let's do the arithmetic. Take the Sun. Its diameter is about 1,392,000 kilometers, roughly 109 times the diameter of Earth. By any human standard, it is enormous. It contains about 99.8% of the mass of the entire solar system. Now, take the distance to the nearest other star. Proxima Centauri sits about 4.24 light years away, which is about 40 trillion kilometers, precisely 4.01 times 10 to the 13th kilometers. Divide one by the other, and you get a ratio of about 29 million to 1. Numbers at that scale stop registering, so shrink the whole thing until it fits in a room. Scale the Sun down to a single grain of sand, 1 millimeter across. At that scale, the nearest other grain of sand is not on the same table. It is not in the same building. It is about 29 kilometers away. Call it 30. 2 grains of sand, 30 kilometers apart, and between them, nothing but a thin haze of hydrogen atoms and dust so sparse it would count as a hard vacuum in any laboratory on Earth. That is the local stellar neighborhood. That is the actual density of the thing we call a galaxy. Now take a second collection of grains of sand, distributed at the same spacing, and pass it through the first one at a few hundred kilometers per second. Ask how many grains touch. The answer over the entire volume of 2 galaxies and the entire duration of a merger is essentially none. NASA's own statement of this from the 2012 release that carried the Destined headline is about as plain as astronomy gets. The stars inside each galaxy are so far apart that they will not collide with other stars during the encounter. The centers are denser than the neighborhood we live in. Near the nuclear star cluster of either galaxy, stars are packed millions of times more tightly than they are here. And in those cores, over the full length of a merger, occasional close passes and even rare direct hits become physically possible rather than merely conceivable. But possible in the densest cubic parsec of a galaxy over 1 billion years is a very different statement from the picture the word collision hands you. So here's the reconciliation, and it is the strangest fact in tonight's episode. In the branch where these 2 galaxies merge, roughly 4 billion years from now for the first close pass and about 6 for the finished object, the Milky Way as a recognizable structure ceases to exist. And nothing in it hits anything. Both statements are true at once. The thing that is destroyed is not matter, it is order. A spiral galaxy is a remarkably ordered object. Most of its stars move in the same plane, in the same direction, on nearly circular orbits, at speeds that vary smoothly with radius. That order took about 10 billion years to establish, and it is maintained by nothing more than the collective gravity of everything in it. It is not held together by any structure. It is a statistical arrangement, the way a river's shape is a statistical arrangement of water. Pass a second galaxy through it, and the statistics change. Orbits that were circular become elongated. Orbits that shared a plane get tilted into every possible orientation. Stars near the outer edge, held most weakly, get pulled away entirely and strung out into tails hundreds of thousands of light years long. The disk does not break, it disperses. Over 1 billion years or two, the ordered rotation that made it a disk is converted into random motion in all directions, and an object whose stars move randomly in all directions is not a spiral. It is an elliptical, and every one of those stars, every single one, completes the entire process without touching another star. There is a further consequence of this that is easy to miss. Because nothing collides, nothing is lost to friction, and the total number of stars in the merged system is simply the sum of the two. Several hundred billion from one galaxy, several hundred billion from the other, all of them still burning, all of them still on the main sequence or wherever their individual life stories had reached. The merged galaxy is not diminished by the process that made it. It is the largest stellar system either of these 2 galaxies has ever been part of. If you want the human scale version, nothing is smashed, everything is rearranged. It is the difference between a building being demolished and a crowd of people leaving a stadium. The building is gone in both senses. The crowd is gone only in the sense that it stopped being a crowd. Stars are not the only thing in a galaxy, and the other thing behaves in the exact opposite way. Between the stars, in the plane of the disk, sits the interstellar medium. Gas, mostly hydrogen, with a small admixture of helium and a trace of heavier elements, plus solid dust grains a fraction of a micron across. By mass, it is a minority component, something on the order of 10% of the visible material in a galaxy like ours. By volume, it is everywhere. The gas is not spread smoothly. It is organized into clouds, and the important ones are the cold, dense, molecular clouds where hydrogen exists as H2 rather than as isolated atoms. A large giant molecular cloud is tens of light years across and contains anywhere from thousands to millions of solar masses of material. The Orion complex, the nearest large example, spans several hundred light years of structure and sits about 1,300 light years away. Now apply the same emptiness test we applied to stars and watch it fail. A star is about 1 part in 29 million of the distance to its neighbor. A giant molecular cloud is tens of light years across, and the typical separation between such clouds in a galactic disk is on the order of hundreds of light years. The ratio is not 29 million to 1. It is something like 10 or 20 to 1. That difference of 7 orders of magnitude is the entire distinction between what survives a galactic merger untouched and what does not. When two galaxies pass through each other, the gas in one runs directly into the gas in the other. It cannot pass through. Gas is a fluid. It exerts pressure. Two streams meeting at a few hundred kilometers per second produce shock fronts, compression, heating, and, critically, a loss of orbital energy. The stars sail through each other's fields and keep their energy. The gas dumps its energy into heat and radiation and falls inward. This is why a merger is violent in one respect and gentle in another, and why the phrase galaxies collide is not entirely a metaphor. The star systems interpenetrate. The gas reservoirs genuinely collide. The consequences of that collision are the most visually dramatic part of the entire event, and they are the reason the sky in this story does not merely rearrange itself. It changes color. Compressed cold gas does one thing above all others. It collapses and forms stars. Star formation is a competition between gravity, which wants to pull a cloud inward, and pressure, which wants to hold it up. A cloud that is stable for 100 million years can be pushed over the threshold by a shock wave passing through it, because the shock raises the density faster than the internal pressure can respond. Once the cloud fragments, the fragments collapse on timescales of hundreds of thousands to a few million years, and the result is a cluster of new stars. A galaxy merger delivers that shock to the entire gas reservoir of two galaxies at once. The observed consequence is called a starburst, and it is one of the most reliable signatures of an interacting pair anywhere in the sky. Star formation rates in merging systems can run 10 to 100 times higher than an undisturbed galaxy of the same mass. The Milky Way currently converts something in the neighborhood of 1 to 2 solar masses of gas into new stars per year, a modest, steady rate. A merger-driven starburst can push a comparable system into the range of tens of solar masses per year, sustained for tens or hundreds of millions of years until the fuel is exhausted. And the light produced by a starburst is not like ordinary galactic light, because the population that dominates it is young. The most massive stars are the brightest and the shortest lived. A star of 20 solar masses shines tens of thousands of times more brightly than the sun and burns through its hydrogen in a few million years. In an ordinary galaxy, those stars are rare because they die so quickly that only a small population exists at any moment. In a starburst, they are being manufactured continuously, and the integrated light of the galaxy shifts strongly toward the blue. Alongside them come the clouds those stars light up. Ultraviolet radiation from young massive stars ionizes the hydrogen around them, and ionized hydrogen re-emits in a deep specific red at 656 nanometers. That is the color of the Orion Nebula, the color of the lagoon, the color of every stellar nursery in every photograph you have ever seen of one. In the merger branch, for a period of a few 100 million years, that is the color of large regions of the sky. None of this is speculative in the way that predictions about the future usually are, and the reason is simple. The universe contains an enormous number of galaxies, and at any moment, some fraction of them are doing this. We do not have to imagine a merger. We can photograph several hundred of them. The most famous example sits about 60 million light-years away in the constellation Corvus, cataloged as NGC 4038 and NGC 4039, and known universally as the antenna. Two spiral galaxies caught a few 100 million years into an encounter, their cores still distinct, their disks already deformed into a tangle. And extending from the pair in a long, graceful curve across a span far larger than either original galaxy, two enormous streamers of stars and gas. Those streamers are the tidal tails that give the pair its name, and they contain material that was, not long ago, part of an ordinary rotating disk. Inside the overlap region between the two cores, Hubble imaging resolves thousands of young star clusters, blue and compact, formed in the compressed gas. That is the starburst, caught in the act. There are others, each one a different frame of the same film. The mice appear in coma Berenices with two long straight tails, caught earlier in the process. ARP 220, a much more advanced merger, so thick with dust that most of its enormous energy output emerges in the infrared rather than in visible light. The cartwheel, where a small galaxy passed straight through the center of a larger one and sent a ring of star formation propagating outward like a ripple on a pond. And in the deep field images, where thousands of galaxies appear in a patch of sky smaller than a grain of rice held at arm's length, interacting pairs are common. Mergers are not exotic events. They are how large galaxies are assembled. The standard picture of structure formation has small systems merging into larger ones repeatedly over cosmic time. And a galaxy the size of the Milky Way is understood to be the accumulated product of many such events. So when we ask what the sky looks like when galaxies meet, we are not entirely speculating. We are describing something that has been photographed many times from the outside and then asking what it would look like from a seat inside one of the two galaxies. That inside view is the one nobody has ever had. Before either disk shows any distortion at all, something else will already have made contact, and it is invisible. Both galaxies sit inside halos of dark matter. The visible disk of the Milky Way is about 100,000 light-years across. Its dark matter halo extends far beyond that, plausibly out to several 100,000 light years, and contains most of the system's total mass. Andromeda has the same structure. The two halos are enormous, diffuse, and nearly spherical, and the distance between the two galactic centers, about 2.5 million light years, is only a modest multiple of their combined extent, which means the outer halos are not distant strangers. On cosmological terms, they are already in contact, and they will overlap substantially long before the disks come anywhere near each other. Dark matter behaves, in this respect, more like stars than like gas. It is collisionless. Two dark matter halos pass through each other without shock fronts, without heating, without any of the fluid behavior of the interstellar medium. What they do instead is exchange orbital energy through a process called dynamical friction. And this is the mechanism that decides whether a merger happens at all. Here is the idea, and it is elegant. As one massive body moves through a sea of smaller ones, it gravitationally attracts the particles it passes, and they pile up in a wake behind it. That wake has mass. Its gravity pulls backward on the body that created it. The result is a drag force, not from any contact, purely from the gravitational response of the medium. Dynamical friction is why a first pass usually leads to a merger, rather than an endless series of flybys. Each passage through the other system's halo bleeds orbital energy into the halo particles. The orbit shrinks. The next pass comes sooner and closer. Over a few oscillations, the two centers spiral together. It is also why the mass estimates matter so much for the prediction. The strength of dynamical friction depends on how much mass is in the halos and how it is distributed. Get the halo masses wrong by a factor of 2, and the timescale for the spiral and changes accordingly. That single uncertainty is a substantial part of the spread in the 2025 result. The most beautiful thing gravity does in a merger is also the simplest to explain, and you can see it in the antennae without knowing any of the mathematics. Gravity weakens with distance. When a large mass passes near an extended object, the near side is pulled harder than the far side, and the difference between those pulls is a tidal force. It stretches the object along the line to the intruder and squeezes it perpendicular to that line. On Earth, this raises 2 ocean bulges a meter high. On a galactic disk, applied for 100 million years, it does something far more dramatic. The outer parts of a disk are the vulnerable parts. A star at the edge of the Milky Way, 60,000 light years from the center, is held by the whole mass interior to it, but held loosely. The gravitational binding at that radius is weak compared with what a star near the center experiences. When another galaxy of comparable mass comes within 100,000 light years, the tidal force at the disk's edge becomes comparable to the galaxy's own hold on those stars. So they leave. Not all at once and not in random directions. They leave in an organized way that depends on which direction they happen to be orbiting when the intruder arrived. Stars orbiting in the same sense as the encounter, prograde, get flung outward into a long, thin, curving stream that trails behind the galaxy. Stars on the opposite side get drawn toward the intruder into a bridge connecting the two systems. That is why the classic merger image has both a tail on the outside and a bridge in the middle. It is not two different phenomena. It is one tidal field acting on stars with different orbital phases. The scale of these structures is difficult to hold in mind. The antennae's tails extend more than 300,000 light years, several times the diameter of the galaxies that produce them. They are extremely thin compared with their length, extremely low in density, and they take hundreds of millions of years to develop fully. And they are made of ordinary stars. If the sun ends up in a tidal tail, and there's a real chance it does, nothing happens to the sun. It continues to burn hydrogen exactly as before, on a new trajectory, carrying its planets with it in a stream of stars strung across intergalactic space. The sky from inside such a stream would be something no one has ever seen. We will come back to that. There is a temptation to treat the Andromeda encounter as a singular event in our galaxy's history. It would not be. It would be the largest one in a long series. The evidence is written into the structure of the halo around us, and reading it has been one of the major achievements of the last 30 years of galactic astronomy. The first clear case was found in 1994. Rodrigo Ibata, Gerard Gilmore, and Mike Irwin identified a population of stars on the far side of the galactic center, moving together at a common distance that did not belong to any known component of the Milky Way. It was a dwarf galaxy, the Sagittarius dwarf spheroidal, caught in the process of being pulled apart. Subsequent surveys traced its debris into an enormous stream of stars that wraps more than once around the entire Milky Way, above and below the disk. That stream is a galaxy that no longer exists as a galaxy. Its stars are now part of ours. The second case is older and much larger. Data from the Gaia mission, which has measured positions and motions for well over 1 billion stars, revealed that a large fraction of the stars in the inner halo share a distinctive signature: highly elongated orbits, all oriented in a similar way, with chemical compositions that mark them as belonging to a system that evolved separately from the Milky Way's disk. The interpretation, published independently by more than one group in 2018, is that the Milky Way absorbed a substantial galaxy roughly 8 to 10 billion years ago. The debris is usually called Gaia Enceladus, or informally the Gaia sausage, after the shape the orbits trace in a velocity diagram. That merger was not a minor accretion. Estimates put the intruder at something like 1/4 of the Milky Way's mass at the time. It is thought to have heated the existing disk substantially, thickening it into the component we now call the thick disk. So the Milky Way's structure already contains the fossil record of at least one major encounter and dozens of smaller ones. The stars are still here. The galaxies they came from are not. That is the pattern, repeated at every scale we can observe. The material persists. The arrangement does not. The same reading has been done on Andromeda, from the outside, which in some ways is easier. In 2001, a survey of Andromeda's outer regions turned up a structure that had no business being there: an enormous stream of stars extending from the vicinity of the galaxy's disk out into its halo, tens of thousands of light years long, with a stellar population distinct from the disks. It is known as the giant stellar stream, and it is understood as the tidal debris of a satellite galaxy that Andromeda disrupted and swallowed, probably within the last 1 billion or 2 billion years. Follow-up work found more. Andromeda's halo turns out to be full of substructure, shells, arcs, and streams that are the settling remnants of past accretions. Some models suggest the entire inner halo has been reshaped by a fairly major merger in Andromeda's relatively recent past, which would explain features that a quiet galaxy should not have. Put the two histories side by side, and the framing of tonight's episode changes slightly. Two galaxies are approaching each other. Both of them are already composite objects, assembled from earlier encounters, carrying visible debris from systems that lost their identity inside them. Neither one is a pristine, original structure that a merger would spoil. This is what large galaxies are. They are the accumulated result of everything they have absorbed, which means that in the branch where the merger happens, the honest description is not that something is destroyed. It is that the process which built both galaxies runs one more time, at the largest scale either of them has experienced, and produces the next object in the sequence. Now we can go to the sky and walk through it stage by stage. Before we move the clock, it is worth spending a segment on what Andromeda actually is, because most descriptions of the encounter treat it as an abstraction, a mass with a velocity, and it is a specific object with specific properties. It is a large barred spiral, catalogued as Messier 31 in Charles Messier's list of things that are not comets, and as NGC 224 in the New General Catalog. Its disk is inclined about 77 degrees to our line of sight, which is why it appears elongated rather than round. We see it nearly edge-on, but not quite, which is the most informative angle for measuring how a galaxy rotates. Its disk is larger than ours. Estimates of its diameter run to something like 150 to 200,000 light years for the full extent, against roughly 100,000 for the Milky Way's bright disk. For most of the 20th century, that size difference was taken to imply a proportionally larger mass, and the older stellar counts, 1 trillion stars in Andromeda against a few 100 billion in the Milky Way, followed from it. Modern work has narrowed that gap substantially. Total mass estimates depend on dark matter halo modeling rather than on visible extent, and by that measure, the two galaxies are much closer to equals, with the ordering depending on which technique you weight most heavily. It is fair to say that Andromeda is somewhat larger and more spread out, and that neither galaxy is clearly dominant. That near equality matters for the merger. A major merger between comparable masses destroys both disks, while a minor merger with a much smaller galaxy leaves the larger one bent but recognizable. It has a retinue. Two satellites are bright enough to appear in the same photographs as Andromeda itself. M32, a compact elliptical sitting close to the disk, and M110, a more diffuse dwarf elliptical offset to the other side. M32 is unusual, extremely dense in its center, and widely suspected of being the stripped remnant of a once larger galaxy that Andromeda has already partially consumed. Beyond those two, dozens of fainter dwarf companions have been catalogued, along with M33 at a greater distance. Its rotation was measured before anyone knew it was a galaxy. Vesto Slipher and later Francis Pease found that one side of the disk is redshifted relative to the other, which means one side is coming toward us and the other is going away. Later work established the flat rotation curve. The outer parts orbit as fast as the inner parts, rather than slowing with distance as they would if the visible mass were all the mass. That was one of the earliest lines of evidence for dark matter, and it came from this same galaxy. So the thing approaching us is not a smooth blob. It is a structured system with a bar, a bulge, spiral arms, dust lanes, satellites, 100 million solar mass black hole, and a halo full of the debris of things it has already eaten. Not everything in a galaxy is vulnerable to a merger. Some structures pass through the entire event unchanged, and identifying which ones is a good test of whether the physics has been explained clearly. The rule is simple. A structure survives if its internal gravitational binding is strong compared with the tidal forces applied to it. By that rule, planetary systems survive completely. The Earth orbits the Sun at 8 light minutes. The tidal force from a star passing at 1 light year is smaller than the Sun's hold on Earth by a factor so large that the perturbation is unmeasurable. Every planetary system in both galaxies comes through intact. Star clusters are the interesting case because they come in two kinds with different fates. Open clusters, the loose associations of a few hundred to a few thousand young stars, like the Pleiades, are only weakly bound. They dissolve on their own within a few 100 million years, even without a merger, simply through the tidal field of the galaxy they orbit in. A merger accelerates this. They do not survive, but they were never going to. Globular clusters are a different object entirely. A globular is a tightly bound sphere of 100,000 to 1,000,000 ancient stars, packed into a region only a few tens of light years across, held together strongly enough that it has survived 10 billion years of orbiting through the galaxy's tidal field already. The Milky Way has roughly 150 known globulars. Andromeda has several hundred. Those pass through the merger essentially unharmed. Their orbits change. They get redistributed through the merged halo, some flung far out, some brought inward. But the clusters themselves remain coherent objects. In the merged elliptical, billions of years later, the globular cluster population would be the combined population of both galaxies, orbiting a system that no longer resembles either. This is not a prediction. It is an observation. Elliptical galaxies formed in past mergers are known to have unusually rich globular cluster systems, often with two distinguishable populations of different ages and compositions, a direct fossil signature of the two galaxies that combine to make them. And at the very center, both nuclear star clusters survive as dense knots long after everything around them has dispersed, sinking together and carrying their black holes with them. The opposite question is also worth asking, because a merger does not only rearrange material, it genuinely loses some. Gravitational interactions between three or more bodies have a characteristic outcome. The system tightens its core and ejects something. Energy is conserved, so if two bodies fall closer together, a third has to carry away the difference, and if it carries away enough, it leaves entirely. In a galaxy merger, this operates at every scale. At the largest scale, the tidal tails themselves. Some fraction of the material pulled into those streams is on genuinely unbound trajectories, moving fast enough in the right direction to escape the merged system's gravity permanently. Those stars leave. They do not come back, and they do not join anything else, because the next galaxy is millions of light years away and receding. They spend the rest of their existence in intergalactic space. We can see this population elsewhere. In rich galaxy clusters, a diffuse glow fills the volume between the galaxies, and it comes from stars that belong to no galaxy at all, stripped out during past interactions and now orbiting the cluster as a whole. Estimates for what fraction of a cluster's stars live outside any galaxy run to something like 10%, and in some systems higher. At the smallest scale, the black hole binary at the center does the same thing more violently. As the two supermassive black holes spiral together, any star that wanders into the region between them gets accelerated by a three-body interaction and flung outward at enormous speed. This is one proposed origin for hypervelocity stars, stars moving fast enough to escape a galaxy entirely, of which several dozen candidates are now known in the Milky Way, some moving at more than 1,000 kilometers per second. The record holder found so far, cataloged as S5HVS1, is moving at roughly 1,750 kilometers per second and was traced back to an ejection from the neighborhood of Sagittarius A about 5 million years ago. One star, thrown out of the galaxy by a single encounter with the central black hole, now on a trajectory that leaves and never returns. A merger would produce many more of those. Not enough to matter for the galaxy's mass budget. The ejected fraction is small, but enough that the space around the merged system would be threaded with stars leaving in every direction at speeds no ordinary galactic orbit can produce. There is a constructive side to all of this that is easy to lose behind the language of destruction, and it concerns the material that planets are made of. The universe began with hydrogen and helium, and almost nothing else. Every atom heavier than that was manufactured, either inside stars or in the events that end them. Carbon and oxygen come primarily from the interiors of stars and are released when those stars shed their envelopes or explode. Iron comes largely from a particular class of supernova. The heaviest elements require even more extreme conditions. Each generation of stars enriches the gas around it, and the next generation forms from that enriched gas. The Sun is a late generation star, and the rocky planets around it exist because earlier stars in this region made and released the silicon, magnesium, iron, and oxygen they are built from. A merger-driven starburst is an enrichment event on a scale a galaxy does not otherwise experience. Tens of solar masses of gas per year converted into new stars for hundreds of millions of years, with a population weighted toward the massive end, and massive stars are the ones that produce heavy elements fastest and return them soonest, because they live only a few million years before exploding. The gas that remains after such a burst is substantially more enriched than the gas that went in, which means the stars that form late in a merger and the planets that form around them are built from better material than the stars that formed early. There is a limit to this, and it is the reason ellipticals are quiet. Eventually, the cold gas is exhausted, converted into stars, blown out by supernovae, or heated to temperatures at which it can no longer collapse. Once that happens, star formation stops, and it does not restart because the fuel is gone and no new supply arrives. The merged galaxy becomes a closed system, slowly reddening as its remaining stars age. So the merger is not simply a rearrangement, and it is not simply a loss. It is the last great episode of construction in the history of this pair of galaxies, a final, enormous burst of star and planet formation, followed by a very long quiet. Whatever forms in that burst will be the youngest thing either galaxy ever makes. Everything from here forward is conditional. This is the merger branch, the roughly 1 and 2 future, and inside it the specific timeline from the 2012 orbit solution, where the first closed pass falls about 4 billion years from now. Hold that condition in place under everything that follows. Start with what is actually overhead right now, because the present is stranger than it gets credit for. Find a dark site in autumn. Locate the Great Square of Pegasus, then follow the chain of stars northeast into the constellation Andromeda. And about 2/3 of the way along, slightly off the line, there is a patch of sky that is not quite black. It has no edges. It does not resolve into anything. If the sky is good, it is unmistakable. If the sky is mediocre, you can convince yourself it is not there. That patch is a trillion-star system, or something close to it by the older counts, seen across 2.5 million light years. Here's the part that never stops being remarkable. The light entering your eye from that smudge left Andromeda about 2.5 million years ago. On Earth at that moment, the genus Homo was in its earliest stages in East Africa. Stone tools were being made, or were about to be. There was no writing, no agriculture, no wheel, and no species alive that would recognize itself in a mirror the way we do. That light has been in transit, unimpeded, across the emptiest environment the universe consistently produces for the entire span of human existence and then some. And it is not a snapshot of Andromeda. It is a snapshot of Andromeda's past. The galaxy has moved about 270,000 light years closer since that light departed, 110 kilometers per second, sustained for 2.5 million years. Everything you are seeing is a report from a position the object has already left. This is true of every astronomical observation, but the delay is usually a technicality. Sunlight is 8 minutes old. The nearest star's light is 4 years old. At 2.5 million years, the delay becomes a real part of the physics. It means we cannot watch the approach happen. We can only measure it and integrate forward. There is one more feature of tonight's sky worth naming before we start moving the clock, because it is the thing that changes most. Across the sky, on a good night, runs the band. Not a cloud, though it looks like one. The combined light of a few 100 billion stars in the plane of our own galaxy, seen edge on from a position about 26,000 light years out from the center. Every civilization that has looked up has named it. It is the single most observed structure in human history. In the merger branch, it does not survive. Before we advance the clock, there is a correction that has to be made, because otherwise everything that follows is dishonest. The sky in this story does not have a human audience. The Sun is a main sequence star, fusing hydrogen in its core, and as it does so, its core slowly contracts and heats, and its energy output slowly rises. The rate is about 1% every 110 million years, roughly 10% per billion years. That sounds gentle. It is not for a planet with liquid water and a thin atmosphere. Detailed climate modeling of this problem has been running since the late 1980s, and the results cluster around an uncomfortable timescale. Somewhere on the order of 1 billion years from now, the increased solar flux is expected to push Earth's climate into what is called a moist greenhouse. Water vapor, which is itself a greenhouse gas, accumulates in the upper atmosphere. Ultraviolet light breaks it apart. The hydrogen escapes to space. The process is not reversible because the hydrogen does not come back, and over subsequent hundreds of millions of years, the oceans thin and then go. 1 billion years. That is the number with real uncertainty attached to it. Some models say 800 million, some say closer to 2 billion, and the answer depends on assumptions about clouds and carbon cycling that are genuinely hard. But the order of magnitude is robust, and it sits 4 times closer than the first close pass with Andromeda. So when we describe the sky at the moment of the encounter, we are describing a sky with no observer on this planet. Earth will still be here. It is not swallowed by anything, and the merger poses no direct threat to the solar system's integrity. But it will be a dry, hot, sterilized world, and it will have been one for billions of years. I want to be plain about why we are going to describe the view anyway. The view is a real physical fact. Light will genuinely arrive at these coordinates in this pattern, whether or not anything is here to receive it. Describing it is not sentimentality. It is a way of making enormous timescales legible, because human vision is the one instrument every listener carries. And if there is anyone anywhere in that future, in this system, or somewhere else in either galaxy, this is what they will see, the convention for the rest of tonight. When I say you would see, I mean an observer standing on a stable platform at the sun's location, with human eyes, and no other claim is being made. Advance the clock 2 billion years. Andromeda is closer, and the arithmetic of how much closer is less impressive than you might expect. At 110 kilometers per second, 2 billion years covers about 730,000 light years. The gap narrows from 2.5 million light years to something on the order of 1.8 million, though in reality, the approach accelerates as the two systems fall, so the true figure is somewhat smaller than the linear estimate. The sky's response to that is modest. Angular size scales inversely with distance, so a galaxy that spans 3 degrees at 2.5 million light years spans something over 4 degrees when the gap has closed by a third. Andromeda would be visibly larger to a careful observer and still unmistakably a smudge. But the surface brightness is what matters for naked eye visibility, and surface brightness behaves differently. As the galaxy comes closer, its total light spreads over a larger area of sky, and the brightness per unit area stays roughly constant. What changes is how much of the faint outer disk climbs above the eye's detection threshold. More of the galaxy becomes visible, not because it gets brighter, but because more of it is large enough for the eye to integrate. By 2 billion years, an observer with dark adapted vision would see an elongated glow, substantially larger than the full moon, with a brighter core and a suggestion of extension along one axis. It would still be a faint object. It would no longer be a marginal one. Meanwhile, the Milky Way's own band is unchanged. 2 billion years is about 8 or 9 orbits of the Sun around the galactic center, and in that time the disk simply keeps turning. The constellations are gone, all of them, many times over, because the patterns we see are accidents of the current positions of nearby stars, and they dissolve on timescales of a few 100,000 years. But the band remains because the disk remains. This is the long, quiet part of the story. Nothing dramatic happens for the first 3 billion years. Two galaxies fall toward each other in silence, and the only visible change is that one of them slowly grows. At 3 billion years, the character of the sky begins to change, and it changes in a way that has no precedent in human experience. The gap is now on the order of 500,000 light years or less, depending on how much the approach has accelerated. Andromeda's angular size has grown past 10 degrees, 20 times the width of the full moon, larger than the bowl of the Big Dipper. And at that scale, the outer disk is bright enough and extended enough that the eye stops seeing a smudge and starts seeing a structure. Think about what that means. Not a point of light, not a fuzzy patch, a resolved object with an identifiable shape hanging in the sky, tilted at whatever angle the geometry of the approach has left it. You would be able to see the dust lanes. Andromeda's disk is threaded with dark bands of dust that absorb the light behind them, and in photographs they are the most striking feature of the galaxy after the core itself. At 10 or 20 degrees across, those lanes would be resolvable, dark curving structures against a lighter background, visible to an unaided eye. You would be able to see the difference between the bulge and the disk. A concentrated, yellowish, roughly spherical center, surrounded by a flatter, bluer, extended sheet. And this is the point in the timeline where a genuinely new astronomical experience becomes available, one no human has ever had. Every extended object our ancestors could see, the moon, the Milky Way's band, the occasional comet, belongs to our own system. To see the internal structure of another galaxy with your eyes, an entire independent system of hundreds of billions of stars, laid out large enough to trace with a finger, is something that has never once happened in the history of anything on this planet. By late in this stage, the tidal effects begin. The outer disks of both galaxies start to feel the other's pull differentially, and the first warps appear. Subtle at first, a bending at the edges, a thickening of the outer regions. Nothing has been torn away yet. The geometry has simply stopped being clean. 4 billion years from now, in this branch, the two galaxies make their first close approach. The orbit solution puts the minimum separation at about 31 kiloparsecs, roughly 100,000 light years. That number is worth pausing on. The bright disk of the Milky Way is about 100,000 light years across. A closest approach equal to the width of the disk means the two systems are not passing at a respectful distance. They are interpenetrating. From the ground, the sky at this stage is unrecognizable. Andromeda no longer fits in a patch of sky. It occupies a substantial fraction of the entire visible hemisphere, tens of degrees across, possibly most of the sky depending on the exact geometry and the observer's position in the Milky Way's disk. Its core is a distinct, bright, extended object, brighter than anything except the sun and the moon. Its disk stretches away in both directions, textured with dust lanes and star clouds. And it is no longer a separate thing from the sky you are standing in. The Milky Way's own band is still there, still running horizon to horizon, but now a second, larger, differently oriented sheet of stars crosses it. Two galactic planes at an angle to each other, both visible at once, overlapping. There is no image in human art that corresponds to this. Every painting of a dramatic sky is a rearrangement of things we have seen. This would not be. The physics happening during this pass is mostly invisible from the inside. The gas disks are running into each other, shocked and compressed, and the first great wave of triggered star formation is beginning. Dynamical friction is stripping orbital energy out of the encounter. The outer stars of both galaxies are being pulled into the beginnings of tidal tails. What an observer would actually notice over a human lifetime is nothing. That is the strange part. Every one of these processes runs on timescales of tens to hundreds of millions of years. A person standing on that hypothetical stable platform for 80 years would see a sky that is spectacular beyond description and completely static. The stars would not move. The galaxies would not visibly approach. You could photograph the sky as a child and again at 80, and the two images would be identical to any precision the eye can judge. Everything in this episode is happening at a speed that makes a human life an instantaneous sample. After the first pass, the two galaxies separate again. They do not escape. Dynamical friction has already taken too much energy out of the orbit. Over the next several 100 million years, the two systems draw apart to a fraction of their original separation, slow, stop, and begin to fall back. And during that interval, the tidal tails develop fully. This is when the sky's basic geometry breaks. A tidal tail is a stream of stars pulled out of a disk and strung across intergalactic space. From outside, in a photograph of the antennae, it is a graceful curved filament. From inside, if your star happens to lie along the direction of a tail, it is something else entirely. A band of light, but not the band you know. Narrower, fainter, running at an angle that has nothing to do with the old galactic plane, because the old galactic plane no longer exists as a coherent structure. Meanwhile, the Milky Way's own band is coming apart. The disk that produced it is being heated. Orbits tilted out of the plane, circular paths stretched into ellipses, and a disk whose stars have random vertical motions is a thick, diffuse structure rather than a thin sheet. The sharp, bright line across the sky broadens, dims, and loses its edges. By the end of this stage, there is no band. There is a general brightening across a broad swath of sky with no clear boundaries. An observer at this stage would live under a sky that is brighter overall than ours, structurally chaotic, and full of features with no names. Arcs, streams, a second galactic core, still distinct, somewhere overhead. Bright knots where new star clusters have formed in the compressed gas. One detail of that sky is worth holding, because it is the moment the episode's title actually resolves. There is a last night on which the Milky Way's band is recognizable as a band, and there is a first night on which it is not, and between them there is no event. No threshold is crossed. The disk simply heats by a fraction of a percent per million years until the structure it produced falls below the threshold of the eye. Everything in this story happens that way, by accumulation, without a moment. And the total amount of light is genuinely higher. More stars are in view because the two populations now overlap. Many of them are young and blue and enormously luminous. The night, at this stage, is not as dark as ours. The starburst is the most visually distinctive phase of the entire process, and it is worth describing carefully because it is where the color changes. Our current sky is dominated, in terms of naked eye stars, by a mixture of old and young populations, and it reads as essentially white with scattered color. Betelgeuse and Antares are visibly orange. Rigel and Spica are visibly blue-white. Most stars sit in between, and the eye's poor color sensitivity at low light levels flattens the rest to gray. In the starburst phase, the balance shifts hard toward the blue end because massive stars are being produced in enormous numbers and massive stars are blue. An O-type star of 30 solar masses radiates in the neighborhood of 100,000 times the sun's output, with a surface temperature around 30,000 Kelvin, and lives perhaps 3 million years before exhausting its fuel. In an ordinary galaxy, at any moment, there are relatively few. In a starburst, there are many, continuously replenished, and they dominate the integrated light of the regions where they form. The visible consequence is a sky with far more bright blue-white stars in it, concentrated in clusters rather than scattered evenly, because they form together and do not live long enough to disperse. Alongside them, the nebulae. The ultraviolet output of these stars ionizes the surrounding hydrogen, which recombines and emits in a narrow red line. To a camera, that is the deep crimson of every emission nebula ever photographed. To a dark adapted human eye, which loses color sensitivity at low intensity, the largest and brightest of these would probably read as pale gray-green patches, the same way the Orion Nebula reads to the eye today, despite being brilliantly red in photographs. But at the scale and proximity implied here, with star-forming regions potentially far larger and closer than anything in the current sky, some of them might cross the threshold into visible color. And the massive stars die. A star of 30 solar masses ends as a core collapse supernova, and a galaxy converting tens of solar masses per year into new stars produces them at a correspondingly elevated rate. The Milky Way currently averages perhaps 1 or 2 supernovae per century, and most are hidden behind dust. In a merger-driven starburst, the rate could be an order of magnitude higher, which means an observer with a long enough life would expect to see new bright stars appear in the sky, hold for weeks, and fade. That is the young sky. Bluer, brighter, knotted with clusters, punctuated by nebulae, and occasionally interrupted by a star that was not there last month. The interval between the first close pass and the final merger is the longest phase in the story, and the least often described, because nothing about it is a single event. In the 2012 solution, the first pericenter falls at about 3.9 billion years, and the merger completes at about 5.9. That is roughly 2 billion years of intermediate state, longer than the entire span from the first complex animals to now, spent in a configuration that has no simple name. What happens during it is a sequence of passes. The two systems separate after the first encounter, decelerate under their mutual gravity, stop, and fall back. The second pass comes faster and closer than the first because the orbit has shrunk. So does the third. Each passage strips more orbital energy through dynamical friction, tears more material into tails, and drives more gas toward the two centers. The gas is the part that changes fastest. Every pass compresses it further, and each compression triggers another burst of star formation, and each burst consumes fuel that does not regenerate. By the end of this phase, much of the cold gas that both galaxies carried for 10 billion years has either been converted into stars or heated to the point where it can no longer collapse. This is one of the standard explanations for why elliptical galaxies are red and quiet. They used up their raw material in the events that formed them. The cores themselves remain distinct for a surprisingly long time. Dense stellar bulges are tightly bound and resist disruption. They sink toward each other through the surrounding material rather than dissolving into it. For a substantial part of these 2 billion years, an observer would see two obvious concentrations of light in the sky: the old Milky Way bulge and the old Andromeda bulge, orbiting each other inside a common, formless envelope of stars. Two centers. One galaxy. That is the intermediate state, and it lasts hundreds of millions of years. Around them, the tails continue to lengthen and thin. Some of the stripped material is genuinely lost, thrown out on unbound trajectories into intergalactic space where it will drift indefinitely. Most of it rains slowly back, falling into the merged system on long, elongated orbits over billions of years, which is exactly how the shells and streams we now see in Andromeda's halo were made. The sky through this whole interval is bright, textured, structurally complicated, and slowly simplifying. Every million years takes a little more of the pattern out and leaves a little more of the smooth glow behind. Somewhere around 6 billion years from now, in this branch, the process finishes, and the result is a galaxy that would be unremarkable if you found it in a survey. The merged system is expected to be an elliptical, a smooth, roughly spheroidal collection of stars with no disk, no spiral arms, no dust lanes, and no organized rotation. Its stars move on randomly oriented orbits, some in, some out, some sideways, with no preferred plane. Its light falls off smoothly from the center outward with no sharp features. Its color is red because the massive blue stars that dominated the starburst have all died, and the remaining population is old, cool, and long-lived. Thomas Cox and Abraham Loeb, in the 2008 simulation paper that did much of the groundwork for this picture, gave the remnant a name that has stuck: Milkomeda. There is something clarifying about the fact that the endpoint is ordinary. Elliptical galaxies are common. The large ones in the centers of galaxy clusters are the biggest stellar systems known, and every one of them is understood to be the product of exactly this kind of history. What we are describing is not an exotic future. It is the standard fate of a large spiral in a group with another large spiral. For an observer inside it, the sky would be defined by what it lacks. There would be no band. That is the change worth holding on to, because the band has been in the sky of every human being who has ever lived. Elliptical galaxies have no plane, so there is no direction in which stars pile up, so there is no line of light. Instead, the distribution of stars across the sky is comparatively even, brighter toward the center of the galaxy and dimmer away from it, but with no edge and no structure. There would be no dust lanes because the dust would be largely gone. There would be few blue stars because star formation would have essentially ended. The sky would be a field of yellow and orange and red points, denser toward one direction and thinning smoothly in the other, with the diffuse background glow of unresolved stars filling the gaps. It would be, in a word, calm. And it would stay that way with very little change for a very long time, tens of billions of years, longer than the current age of the universe, because there would be nothing left in the system energetic enough to disturb it. The solar system does not have a reserved seat in any of this, and the 2012 orbit paper actually put numbers on where it might land. In the models where the merger happens, the Sun has about an 85% probability of ending up at a larger distance from the galactic center than its current 26,000 light years. That is the single most likely outcome, and it makes sense. The merger converts ordered rotation into random motion, and random motion at a given energy carries stars outward. There is roughly a 10% probability that the Sun ends up beyond 50 kiloparsecs, more than 160,000 light years from the center, which is well out into what is now the halo, in territory that currently contains almost nothing but globular clusters and stripped streams. There is a smaller but real chance in the same modeling of the Sun spending some part of the next 10 billion years inside the volume occupied by M33. And Cox and Loeb simulations added a possibility that is stranger than any of those. The Sun might end up in the tidal tail, not orbiting the merged galaxy in the ordinary sense, but strung out in one of the long streams of stars pulled into intergalactic space during the encounter. Through all of this, nothing happens to the solar system itself. That is worth stating clearly, because it is counterintuitive. The Sun's gravitational hold on its planets is overwhelming at these distances. The nearest star during the merger, even in the densest phase, would still be measured in light years. A star passing at 1 light year would perturb the Oort cloud, the shell of icy bodies extending perhaps a light year or more from the Sun, and could send a wave of long-period comets inward over subsequent millions of years. That is a real effect, and it is the most plausible physical consequence of the merger for this specific solar system. But the planetary orbits, packed within a few light hours of the Sun, are untouched by anything short of an extraordinarily close stellar encounter, and the probability of one of those remains small even in a merger. The Sun keeps its planets. It keeps its brightness curve. It simply ends up somewhere else, in a galaxy with a different shape, under a sky it would not recognize. At the center of the Milky Way sits Sagittarius A, a black hole of about 4.3 million solar masses. Its mass measured by tracking individual stars through complete orbits around it over 3 decades, and its shadow imaged directly by the Event Horizon Telescope in 2022. At the center of the Andromeda sits a considerably larger one. Dynamical measurements using Hubble spectrograph, published by Ralph Bender and collaborators in 2005, put it somewhere in the range of 110 million to 230 million solar masses. Call it 100 million, and remember that it is a range, not a number. In the merger branch, those two objects end up in the same galaxy, and then they end up in the same place. The mechanism is the same dynamical friction that brings the galaxies together, applied at a much smaller scale. Each black hole sits inside a dense stellar core. As the cores sink toward the center of the merged system, the black holes sink with them. Once they are within a few light years of each other, they form a bound binary, and the binary begins to shrink. First, by flinging away individual stars that wander too close, each ejection carrying off a little orbital energy, and eventually, when the separation becomes small enough, by radiating gravitational waves. The final coalescence, when it comes, would be one of the loudest gravitational wave events the universe produces. It is also the part of the story with the least certain timescale, the intermediate stage where the binary has ejected the stars available to it, but has not yet tightened enough for gravitational radiation to take over, is a long-standing open problem in the field. Depending on the shape of the surrounding stellar distribution and the amount of gas available, the process might take a few 100 million years, or it might stall for far longer. There is one more possibility worth naming, hedged appropriately. Mergers drive gas toward galactic centers, and gas falling onto a supermassive black hole releases energy with extraordinary efficiency. If enough gas reaches either black hole during the encounter, it could light up as an active nucleus, a compact source outshining the entire stellar population of the galaxy around it. Whether that happens in this particular merger, and how brightly, depends on how much cold gas survives the earlier bursts of star formation. It is a plausible outcome rather than a predicted one. But in the futures where it does occur, the sky acquires a single point of light near the galactic center that is brighter than every star in it combined. Of all the positions a star could occupy during and after this event, the strangest is the tidal tail, and it is worth describing because it inverts everything about the sky we know. Picture a star strung out in one of those streams, 100,000 light years or more from the merged galaxy, moving slowly outward along a filament of stars that were, until recently, part of an ordinary spiral disk. Look in one direction and you see the galaxy, an enormous structured object, a merging pair, or a settled elliptical spanning tens of degrees of sky, bright enough to cast shadows on a planet's surface. The whole thing at once, from outside, which is a view no one has ever had of the Milky Way and never will from inside it. Look in the other direction, and you see almost nothing. Intergalactic space, from a position in a tidal tail, contains a scattering of nearby stream stars, and then nothing until the next galaxy, and the next galaxy is very far away and getting farther. The sky in that hemisphere would be genuinely almost completely dark. A handful of points, a faint smudge or two, blackness across the great majority of it. There are stars like this already, and we can see them. The intracluster population of galaxy clusters, stripped from their parent galaxies during past interactions and now drifting in the space between them, detectable as a faint diffuse glow filling the volume of a cluster. Something on the order of a tenth of the stars in a rich cluster may live outside any galaxy at all. And there's one thing such an observer could do that nobody in a galaxy can. From inside a disk, we have to reconstruct the shape of the Milky Way indirectly by counting stars in different directions, by measuring velocities, by mapping gas, by inference from what other galaxies look like. It took until the 20th century to establish that we live in a spiral at all, and the details of our own spiral structure are still argued over. From a tidal tale, none of that would be necessary. You would simply look. The word for that is not lonely, because loneliness is a property of the observer, not the position. But it is a genuinely different physical situation, and it is worth holding for a moment. A star at the edge of a tidal tail is in the same universe you are in, made of the same material, burning the same fuel. Its sky simply contains one galaxy and one great darkness, and nothing to suggest that either used to be otherwise. There is a second timeline running underneath everything in this episode, and it belongs to the Sun. The Sun formed about 4.5 billion years ago. It will remain on the main sequence, fusing hydrogen in its core for something on the order of 5 billion more. After that, its core hydrogen runs out. The core contracts, hydrogen fusion moves to a shell around it, and the outer envelope expands enormously. The Sun becomes a red giant, hundreds of times its current radius, thousands of times its current luminosity, and cool enough at the surface to glow orange rather than white. Compare the two clocks. First close pass with Andromeda, in the merger branch, about 4 billion years. Merger complete, about 6 billion years. Sun leaves the main sequence, about 5 billion years. Those numbers are not identical, and the error bars on all three are substantial. But they are the same order of magnitude, and that near coincidence is the most quietly remarkable fact in the whole subject. The end of the Sun's stable life and the end of the Milky Way's shape are scheduled, as far as anyone can tell, for roughly the same era. There is no physical connection between them. The Sun's evolution is set by nuclear physics in its core and would proceed identically in an isolated galaxy. The merger is set by gravity and initial conditions on a scale a billion times larger. The two clocks were started by completely different processes and have nothing to say to each other. They just happen to run out together. And here's the thing worth saying plainly about that. It means there is no version of this story in which anyone watches the whole thing from here. Not because the sky becomes hostile, but because the platform expires on the same schedule as the show. Earth's surface becomes uninhabitable roughly a billion years from now, 4 times before the first pass. The Sun's expansion arrives around the time the merger is finishing. Everything we have described is a sky over an empty world, lit by a star that is running out of the thing that makes it a star, in a galaxy that is being taken apart and reassembled. All three processes proceeding independently, on the same enormous timescale, none of them aware of the others. Step back far enough, and there is a larger process running underneath all of this, and it works in the opposite direction from everything we have described. The universe is expanding, and on current models, the expansion is accelerating. Galaxies that are not gravitationally bound to each other are being carried apart, and the rate at which they separate increases with distance. Structures that are bound, like the local group, are exempt. Gravity has already won locally, and the expansion of space does not pull apart a system that has collapsed out of the general flow. That creates a very clean division in the far future. Everything in the local group stays. That means the Milky Way, Andromeda, M33, the Magellanic Clouds, and the several dozen dwarf galaxies orbiting the two large spirals, more than 80 known members and rising as surveys get deeper. All of it remains bound, and over tens of billions of years, most of it will merge into the central object. Everything outside the local group goes. The Virgo cluster, about 50 million light years away and containing more than 1,000 galaxies, is not bound to us. It will recede. So will everything beyond it. As the recession velocity of a distant galaxy approaches and exceeds the speed of light, which is entirely permissible because it is space itself expanding rather than the galaxy moving through space, its light stops being able to reach us at all. It redshifts toward zero energy and fades out. Kentaro Nagamine and Abraham Loeb worked through the consequences of this in the early 2000s, and the picture is stark. On a time scale of roughly 100 billion years, the observable universe from inside the local group empties out. Not gradually thins, empties. What remains is a single galaxy, the merged remnant, Milkomeda plus everything else it has absorbed by then, surrounded by an entirely dark sky. That is the end point of the process that begins with a smudge in the constellation Andromeda. Two galaxies become one. The one becomes everything there is to see. There is a consequence of that emptying which deserves its own segment because it is the most philosophically uncomfortable idea in modern cosmology, and it comes directly from the merger story. Almost everything we know about the universe at large came from looking at other galaxies. We know the universe is expanding because Slipher and then Hubble measured the redshifts of galaxies and found that distant ones recede faster. We know its age roughly because we can run that expansion backward. We know it began hot and dense because we can detect the leftover radiation from that era, filling the sky at a temperature just under 3 Kelvin. We know its composition, its geometry, and its history because we can compare many galaxies at many distances, which is to say, at many ages. Every one of those measurements requires something outside our own galaxy to look at. Now consider an astronomer in Milkomeda, 100 billion years from now. She is a careful observer with good instruments. She looks up and sees one galaxy, hers, and beyond it, nothing. No other galaxies. No redshift distance relation, because there is nothing at a distance to measure. The cosmic microwave background has been stretched by expansion to wavelengths so long and intensities so low that it is undetectable in practice. Everything she can observe is consistent with a single, static, isolated island of stars in an empty and unchanging void. She would not be able to discover the expansion of the universe. She would not be able to discover the Big Bang. Her cosmology, built with perfect rigor from all available evidence, would be wrong in every important respect, and there would be nothing in her sky to tell her so. Nagamine and Loeb made this point, and Loeb has returned to it since, and it functions as a warning about our own position. We happen to live in an era when the evidence is still visible. The universe is roughly 14 billion years old. The acceleration has not yet erased the distant sky, and we arrived in time to see it. That is not a permanent condition. It is a window, and windows close. Which raises a question worth sitting with rather than answering. What is already gone from our sky that we would need in order to understand something we currently cannot? Step back from the specifics, and there is something that should be surprising about this entire episode, and it is that any of it can be said at all. We are describing the configuration of two galaxies containing hundreds of billions of stars each, 4 to 6 billion years in the future, and doing it with named numbers and honest error bars. That is an extraordinary thing for a species that has had telescopes for 400 years and spectroscopy for less than 200. It is possible because of a specific and slightly lucky combination of facts. Gravity is simple. Newton's law of gravitation has one constant and one form, and for objects moving slowly compared with light in weak fields, which describes everything in a galaxy merger, it is accurate to far more precision than the problem requires. There is no complicated physics in the interaction of two galaxies. There is one force applied to an enormous number of bodies. Galaxies are collisionless. Because stars essentially never hit each other, the entire system can be treated as a smooth distribution of mass evolving under its own gravitational field. That is a far more tractable problem than a fluid, and it is why N-body simulations of galaxy mergers were producing recognizable tidal tails as early as 1972 on computers with less memory than a modern thermostat. And the timescales are long. Nothing in a merger happens fast enough to require fine time resolution. A simulation can take million-year steps and lose nothing. So the physics cooperates. What does not cooperate is the initial conditions, and that is the whole content of the 2012 to 2025 revision. The equations are not in doubt. The positions, velocities, and masses that get fed into them are uncertain enough that the answer spreads out. This is the general shape of prediction in the physical sciences, and it is worth recognizing when it appears elsewhere. A confident equation with uncertain inputs produces an uncertain output, and no amount of confidence in the equation repairs that. The honest response is not to pick the most dramatic branch and present it as the answer. It is to report the distribution. The answer is not fixed, and it will move, and the specific measurements that would move it are known. The largest single lever is the mass of the Large Magellanic Cloud. Its perturbation of the Milky Way's motion is one of the main reasons the merger probability dropped, and its mass has been revised upward substantially in recent years on the basis of its effect on stellar streams in our halo. Pinning that number down through better modeling of those streams, better proper motions for its own stars, and better constraints on its orbital history would tighten the whole calculation. The second lever is the total mass of the local group, and specifically the split of that mass between the Milky Way and Andromeda. This is what the timing argument tries to get at, and it remains uncertain at the tens of percent level. Every improvement in halo mass estimates propagates directly into the strength of dynamical friction, and therefore into how quickly a first pass becomes a merger. The third lever is Andromeda's transverse velocity itself, which is still the hardest measurement in the problem. The 2012 value came from an 8-year Hubble baseline. Gaia has since contributed measurements of M31's brightest stars, and combining the two data sets has already refined the vector. A longer baseline helps enormously. Proper motion accumulates linearly with time, while the measurement error does not. So a 20-year baseline is substantially better than a 10-year one for the same instrument. And there are instruments coming. Extremely large ground-based telescopes with adaptive optics can do astrometry at precisions that were not available in 2012. Space-based infrared observatories can resolve stellar populations in M31 with high positional accuracy. Every additional year of Gaia-class astrometry lengthens the baseline for everything already measured. None of this is exotic. It is patient, incremental, unglamorous work, the same category of work that produced the original measurement over 8 years of Hubble time. My expectation, stated as judgment rather than as a result, the probability will move, possibly a lot, and the direction is genuinely unknown. Anyone who tells you confidently which way it will go is telling you about their preferences rather than about the data. We have spent most of tonight inside the merger branch. The other branch is roughly as likely, and it deserves its own description because the sky does something different and nobody ever tells this version. Suppose Andromeda's transverse velocity is at the larger end of its allowed range, or the LMC's tug is stronger than the central estimate, or the local group's mass is at the low end. In that case, the first approach is not a near head-on fall. It is a wide pass. The two galaxies still come close by extragalactic standards, hundreds of thousands of light years, perhaps, but not close enough for the disks to interpenetrate. Tidal forces still act. Both disks would be warped and their outer regions disturbed, and there might be a modest bridge of stripped material between them. But the cores would sail past each other and continue on. The sky in that version is the more beautiful one, in a sense, and it is certainly the more prolonged. Andromeda would grow in the sky for billions of years exactly as described. Smudge, then structure, then an enormous tilted disk filling a large fraction of the visible hemisphere. It would reach its maximum apparent size at closest approach, and then, over the following billions of years, begin to shrink again as the two systems separate, and the Milky Way would keep its band. Warped at the edges, thickened, disturbed, but recognizably a disk with a plane and a bright line across the sky. Two spiral galaxies, both intact, both bent, receding from each other on a long elliptical orbit, bound for another approach in some tens of billions of years. Because even in this branch, they do not escape. Bound is bound. The orbit is longer and the passes are gentler, and on standard dynamical friction grounds, a bound pair that keeps passing through each other's halos is expected to spiral together in the end. I want to be careful with that word, expected. It is the physics of the mechanism, not a number from the 2025 study, which stopped its accounting at 10 billion years and made no claim about what lies past it. That distinction matters, and it is easy to lose. The finding is not that the Milky Way and Andromeda will miss each other forever. The finding is narrower. There is only about a 50% chance they merge in the next 10 billion years, and only about a 2% chance of a head-on collision in the next 4 to 5. Beyond that window, the honest position is that the mechanism points one way, and nobody has put a probability on it. Numbers this size resist meaning, so it is worth doing the work of scaling them once, carefully, before we close. The first close pass in the merger branch is about 4 billion years away. The Earth is about 4.5 billion years old, so the interval between now and the encounter is comparable to the entire history of this planet. Every geological era, every ocean, every mountain range, every extinction, all of it, run again from the beginning. Complex animal life is about 600 million years old. 4 billion years is nearly 7 times that. If you compress the entire history of visible animals on Earth into a single year, the wait for Andromeda would run just under 7 years. The dinosaurs' extinction was 66 million years ago. 4 billion years is about 60 times that interval. Anatomically modern humans have existed for something on the order of 300,000 years and recorded history for barely 5,000. 4 billion years is more than 13,000 times the age of our species, and roughly 800,000 times the length of everything that has ever been written down. And that light in the constellation Andromeda tonight is 2.5 million years old, old enough to predate the species entirely, and yet, against the timescale of the approach itself, essentially instantaneous. The travel time of the light is about 1 part in 1600 of the wait for the arrival. Here's what that ratio actually means. We have caught this system at an arbitrary moment. There is no sense in which we are watching the approach begin, or watching it conclude, or watching anything at all. We are taking one still frame out of a film that is billions of years long, and from that single frame, by measuring how much the colors of the light are shifted, we have worked out the direction the film is running. That is a genuinely extraordinary thing to be able to do from one frame. And it is worth noticing that the frame we got is a good one. Early enough that the distant universe is still visible and cosmology is still discoverable. Late enough that we exist. Long before the sky rearranges itself into something with no band and no neighbors. We have talked about a smudge in the constellation, Andromeda, that most people have never deliberately looked for, and about the fact that it is the most distant thing the unaided eye can reach. We have talked about Vesto Slipher on a hill in Arizona in September of 1912, photographing a spectrum for hours across multiple nights and finding every spectral line shifted toward the blue, the first velocity ever measured for a spiral nebula, 13 years before anyone knew what a spiral nebula was. We have talked about the blind spot in that measurement, that a spectral shift gives you motion along the line of sight with great precision and motion across it not at all, and that the sideways component was the quantity the entire future depended on. We have talked about 8 years of Hubble imaging, from 2002 to 2010, measuring the drift of Andromeda's stars against background galaxies, and producing a transverse velocity of about 17 kilometers per second against an approach of 110, the measurement that made 2012 sound certain. We have talked about the word destined and about the 41% of Monte Carlo orbits in that same paper that actually produced a direct hit. We have talked about the third and fourth bodies, M33 pulling the pair together, the Large Magellanic Cloud pulling the Milky Way off the orbital plane, and a system poised close enough to a knife edge that both of them matter. We have talked about 22 variables and 100,000 simulated futures, and a merger probability near 50% over 10 billion years, and a head-on collision probability near 2% in the next 4 to 5. We have talked about what does not collide. Grains of sand 30 kilometers apart, stars passing through stars for 1 billion years and never touching, order destroyed and matter untouched. We have talked about what does collide. Clouds of cold gas tens of light years across, with only hundreds of light years between them, shocked and compressed and converted into new blue stars at 10 to 100 times the ordinary rate. We have talked about the sky, stage by stage, the smudge, the structure, the dust lanes visible to a naked eye, 2 galactic planes crossing at an angle, the band broadening and dissolving, the young blue sky of the starburst, and finally the smooth red glow of an elliptical galaxy with no plane and no line across it. We have talked about the sun's own clock, running out on the same scale as the merger, and the billion-year deadline on Earth's oceans that arrives 4 times sooner than any of it. And we have talked about the other branch, the 50% where they miss and pass, and come back later anyway, because bound is bound. So here's the answer to the question this episode was named for. The sky does not break. It does not tear or burn or fill with collisions. Nothing in it strikes anything else. What the sky does when galaxies meet is lose its geometry, slowly, over a span so long that no observer could ever perceive the change within a lifetime or within 10,000 lifetimes. It happens in a specific order. First, a smudge grows. For 3 billion years, the only visible change is that a faint patch in one constellation becomes a larger faint patch, then a bright one, then an object with structure, dust lanes, a bulge, a disk you could trace with a finger. Nothing else in the sky moves. Then, for a few 100 million years, there are 2 skies at once. The band you know, running horizon to horizon, and a second galaxy crossing it at an angle, filling a substantial fraction of the hemisphere, so large it has no edge you can take in without turning your head. Then the band goes. Not suddenly. The disk that makes it is heated and stirred until its stars no longer share a plane, and a line of light with no plane behind it becomes a broad glow, and then a general brightening with no boundaries at all. Somewhere in that interval, the last night on which a person could have pointed at the Milky Way passes without anyone noticing, because there is no one there, and because the change from one year to the next is smaller than any eye could measure. Then, for a few 100 million years more, the sky is young. Blue stars in clusters formed all at once out of compressed gas, nebulae glowing where their ultraviolet light strikes hydrogen, new stars appearing, holding for a few weeks, and fading, supernovae, at 10 times the ordinary rate. And then it goes quiet. The gas is spent. The blue stars are gone. They were never built to last. What remains is an even scattering of old red and yellow points across a smooth sky, brighter toward one direction and thinner toward the other, with no line, no plane, no arms, and no dust. A calm sky, a sky that stays that way for tens of billions of years, until the last galaxies outside it have receded past visibility, and there is nothing beyond it at all. That is what the sky looks like when galaxies meet. It looks like the same stars, in a different order. That is also, in the end, the only kind of change this universe reliably performs. Not creation from nothing and not destruction into nothing. Those are rare and difficult. Rearrangement is the common operation. The stars in the merged galaxy are the same stars. The atoms in them are the same atoms. What is lost is a pattern. The flattened, rotating spiral arrangement that 10 billion years of gravity happened to produce, and that a few hundred generations of human beings happened to be born under and to name. You are living inside one of those patterns right now, and not only the galactic one. The arrangement of continents you learned as a child is a slow snapshot of moving plates. The set of species alive today is a frame from a film. The constellations, which look like the most permanent things in the sky, dissolve entirely in a few 100,000 years, the Big Dipper included, its stars drifting apart until the shape is gone. And that happens 15,000 times over before Andromeda even arrives. None of that is a loss in the sense the word usually carries. The material persists. The pattern is what moves. And the fact that a pattern is temporary has never been a good reason to find it less worth looking at. If anything, it is the entire reason it is worth looking at tonight, rather than assuming it will keep. Which brings the whole thing back to where it started. There's a smudge in the constellation Andromeda. It is the most distant object your unaided eye can reach. It is a galaxy of several 100 billion stars, and it is falling toward us at about 110 kilometers every second. That much is measured. Slipher caught it on a photographic plate in 1912. Nobody has ever found a reason to doubt it. Whether it arrives head-on and whether the two galaxies become one is a 50-50 question with a 2% tail in the next 4 billion years. And the honest answer is that we do not know and may never know with certainty. What we do know is the direction. The gap is closing. It has been closing since before anything on this planet had eyes. The band overhead is temporary. The stars in it are not. Nothing in it will ever touch anything else. And the light from Andromeda that will reach this place on the night the sky finally changes left, that galaxy long before any of it happened. The same way the light in your eye tonight left before there were people and crossed 2.5 million light years of almost nothing and found you anyway. It is still on its way, all of it, every night. Good night.